Alright, hello everyone, I'm Bernd and today is day 8 of Advent of Code. So today's puzzle was all about a grid of trees, so we give them a grid and each number represents the height of one tree. And then we care about which trees are visible from the outside of the grid. So tree is visible if there's no taller tree in front of it and no tree of equal size in front of it. So for example, if we look from the left, the first tree would be visible because there's no tree in front of it. The second tree of height 0 would not be visible because there's a higher tree in front of it. Then again, the tree of height 3 would also not be visible because there's another tree of height 3 before it. And then height 7 would again be visible because it's the highest seen so far, and so on. Yes, and then we care about which trees are visible from any side. It could be like left, top, right, or bottom. And we want to then count the number of visible trees inside the grid. So let's have a look at the code. So first, of course, we need to read the file and split it into lines. And then from those lines, we want to get a grid representation. So for us, we define a grid as a dictionary, and this takes the input, the positions, which is a tuple of two integers, and it returns the height of the tree at that position in the grid. And with this, I start with having it as an empty dictionary, and then we go through all the lines and through all the chars like characters in the line, and we keep like track of the index as well, both the line index and the index within the line, and then we set the grid at the corresponding position, height, width, as the integer value of this tree height string. That's how we define the grid, and then we want to iterate for the grid, and because that can be a bit annoying, we put it all into one class. So what is this grid iterator class doing? We start by initializing it with the width and the height of the grid. And then we define methods such as row from left. So that iterates through a row starting from the left of a particular row number. So it gives all the positions in this row starting from the left. So we have all this like row number and column number. And the column number here is in the range of self width. So it starts from 0 and goes all the way to width minus 1. So this gives all the positions within a line. Similarly, we might want on the position in a row from the right. And this again, we return all the tuples of row number and column number. But this time the column number starts at the last index, which is width minus 1. And then until it goes until it reaches minus 1. And it's always decremented. So it goes like from width minus 1 to 0. So that gives us all the coordinates from a row starting from the right. Similarly, we want to iterate for a column with a particular column number, which gives all the coordinates starting from the top. And we also want to iterate for a column from the bottom, which again gets all the coordinates starting, but this time the indices from the range are again reversed. Okay, and then we also want to iterate not just for one row, but for all the rows from the left. So there it just returns every single row. So for each row number in every possible row number, which is range of self height, we return this self row from the left of the corresponding row number. Similarly, we want all the rows. We've iterated from the right, all the columns from the top, for all possible column numbers, and so on. And then with this iterator, it's not too hard to solve the problem anymore. So we first define a grid by this get grid function from lines. Then we also want to know the width and the height of the grid. We get this as the length of the first line and the length of the lines. Then we define the grid iterator, so we can easily iterate for the grid. And then we define this dictionary is visible, which has the same keys as the grid, which is all the positions. And for each positions, you set it to false at the beginning. And then we go through all rows in this rows from left. So this will be iterated from a row. And then we update visible based on the grid. And what we update is visible. And we base it on the current row. And afterwards, we go, we iterate. They consider the rows, but starting from the right. And for each row, again, we update visible based on the current row. And then we also take the columns, once from the top and once from the bottom, and update the visible based on what's visible from the top or from the bottom. So what does this update visible function do? So we have the grid, which gives us the heights of the trees. We have this is visible array, which will be updated. And we have the corresponding line, so that could be either a row or a column and iterated from either side. And then we want to keep track of the highest so far, because the trees of height 0, we want to start at minus 1. And then we go through all the positions in the line. So if the grid at position, so that's the height of the current position, is larger than the highest so far, this tree will be visible from that particular direction. So we said it's visible from that position to true. So if it's already visible from another position, it might already be true, but this doesn't change it then. And if it's not yet visible from another direction, we'll set it from false to true. And then we also need to update the highest tree seen so far, which is then will be the current height, so the grid at the current position. Yes, that's then, yeah, so this way we can always, from the left, we can update the grid, and we update it from based on the rows, but this time from the right. We also can update the visible based on the columns from the top and from the bottom. And then this gives us all the visible trees. In this is visible will be true for those position. And then in order to sum all the count the number of visible trees, we can do this trick where we consider all the values. So this would be a Boolean array, and then taking the sum is the same as counting the number of trues or positive one values. We can do a little test. We have this test input given, and we know ideally it should be 21 trees visible. And if we run the test, it looks very promising. So we can also run it on the tree inputs. And it turns out it also works out. So for the second part, it's slightly different. This time we don't care about what's visible from the outside, but it's like how far we can see from our imaginary tree house that's on the top of a tree. So for example, if we consider this 5, we want to know in each direction how far we can see. So we cannot look up because we have like a ceiling, so we can only look down. So as soon as we see a tree that's as high or higher than the tree we currently at, then we won't see any further. So for example, in the left direction, we see 1 far because this tree already blocks the view for any further tree, and it's also the end of the grid, I guess. Up, we also only see 1 far because it's the same height. To the right, there's no tree blocking the view, so we can see 1, 2, 3 far. And down, again, the first one is lower than the current one, so we see further, and then this 5 would block any further view, but it's also the end of the grid. So we see like in this direction 1 far, in this direction 1 far, in this direction 3 far, in this direction we see 2 trees far. And that's what we want to figure out for part 2. So we can use a lot of things from part 1, in particular read lines, the function getGrid, which takes the lines and defines a grid from it, and the grid iterator. So again, we get our grid. In order to solve the problem, we get this width and the height, and then we define a grid iterator. And then the number of trees we see to the left, we calculate that by this function getTreeSeen based on the grid, and we define a particular grid iterator in the order we want to process the things, which in this case would be rows from the left. And then we also define the trees seen from the right, and so on. How do we do this, or what does this getTreeSeen function do? So it pretty much has the grid, and the grid iterator gives the order of iteration, how we iterate through particular lines. So for each line in the grid iterator, we have this dictionary trees seen per height. Let's start with this. So the trees seen will be a dictionary, and it takes in a position, which is two tuple of integers, and returns how many trees we see from the position in the corresponding direction. So for example, if we look left, this will be how many trees we see to the left. And then for each line in the grid iterator, we define this dictionary trees seen per height. So that's depending on what the next height is. So it could be anywhere from 0 to 9, which is allowed trees height. How many trees we will see to the left in the particular direction given by the grid iterator. So at the very first, if we start and consider the direction to the left, there's no trees to the left. So no matter the height, we will always see 0 trees to the left. And then we go for each position in the line. And the current height will be given by the grid at this position. And then we set like trees seen from the position to this trees seen per height of the current height. So that's just kind of what we define trees seen per height as. And then we need to update this dictionary so that's still true for the next position. How do we update this? So we have this dictionary trees seen per height, and we have the current height. And then for the next height, anywhere in the allowed values, so that's from 0 to 9, we check if the next height is smaller or equal to the current height, then for the next height, we will only see one step to the left because the only tree we will see the current tree, but that's already so high that we can't see any other trees. So in this case, the trees seen per height of the next height will be 1. Otherwise, if the current tree is smaller than the next tree, from the next tree we will see any tree we would have seen from the current position and the current position. So we will see so it just increases the value per 1 for the trees we see per height. And yeah, that's how we update this dictionary. And with this, then it will, for the next iteration, will again give the right values so that we can see the number of trees seen to the number of trees seen depending on the current height. And this is the big advantage, that we need to only go through the grid once in order to calculate the function. We don't need for every position we need to go through the grid or through multiple lines or something like that. Okay, so that's the way to calculate the tree seen in a particular direction. So it's given by this iterator. So did we use that to calculate the trees we see to the left for particular the trees we see to the right, the trees we see to the up in the direction up, and the trees we see in the direction down. And then what we care about is the scenic score. So the scenic score calculates as the number of trees seen to the left, times the number of trees seen to the right, times the number of trees seen in the up direction, and the number of trees seen in the down direction. We want to know the best scenic score, so again we set it to 0. And then for each position, we calculate the scenic score. If the scenic score is better than the best scenic score seen so far, we update the best, and then the solution will be the best scenic score. Yeah, that's it for part 2. We can run a little test to make sure we didn't mess anything up. That looks good. And if we run it on the original input, it also gives us the right result. Okay, that's it for today. Hope you enjoyed the puzzle. Best of luck for the future, and see you around.